Good morning all. I am Dr. D. Madhavi. Today we are going to discuss searching techniques in data structures, the scope of our syllabus. The next one is the binary search. It is more efficient than the linear search. This algorithm works by repeatedly splitting the array into two segments, one going from left to mid and the other going from mid plus 1 to right. That is, the entire array is split into two halves at the middle position, and elements from 0 to mid are taken as one partition, and elements from mid plus 1 to the end of the array are taken as the second partition. So mid is the position halfway from left to right, and where initially left and right are the leftmost and rightmost positions of the array. And one requirement in binary search is all the elements are to be sorted beforehand only before applying this algorithm. So because the array is sorted, it is easy to see which of each pair of segments the search for item X is in. And the search can be restricted to that segment only. That partition only the search can be confined. Moreover, because the size of the subarray going from locations left to right is halved at each iteration of the while loop, we only need log n steps in either the average or worst case. So this is the procedure. This assumes we are given a sorted array A of size n and the key value is x. And we are using the integers left and right. Initially left is set to 0 and right is set to n minus 1, the maximum slot. And another value is the mid. So we are using a while loop. While left is less than right. Okay, when this is valid, that is the first position is treated as left. So while left is and this is the maximum position, last position. So while left is less than right, you set the mid to the integer part of this left plus right by 2. And if x is greater than a of mid, then set left to mid plus 1. Otherwise set right to mid. If a of left is equal to x, then terminate returning left. Otherwise terminate returning minus 1. So first of all, when you receive a key, you compare it with the middle element. If there is a match, the search is successful. If there is no match, then see if the key element is less than mid. If it is less than mid, it goes to the first partition and your search confines only to the first partition. If it is greater than mid, then your search is confined only to the second partition. At any point of time, half of the array length will be skipped from comparisons. So this is the procedure program for binary search. So initially we have taken in A these elements. So 1, 2, 3, 4, 5, 6, 7, 8, 9 elements are there. So n value is 9 and the key element is 79. We have to check whether 79 is there in this array or not. So initially we have taken these three integer values. Left is equal to the minimum element in the array, and then right is equal to maximum position in the array, and an integer mid. While the minimum position is less than maximum position, you have to repeat all these steps. Every time you calculate the mid element and compare the key element with the mid element. If x is greater than a of mid, then left is assigned. That is, the minimum border is shifted to mid plus 1. Otherwise, the maximum border is shifted to mid. So this is first partition and this is second partition. So this entire splitting process continues until you find out the match. So if A of left is equal to X, then return left. Else return minus 1. Minus 1 indicates that the search is unsuccessful. So here this is an algorithm. Sorry, this is an example for the binary search algorithm. So this is an array having 8 elements. And we would like to see whether the value 15 is there in the data set or not. So the key element is 15. So let's narrow our search by finding whether the value is in the first half or in the second half. You find out the mid, and the mid is 9, and then your key element is 15. So 15 is greater than 9. So I'm going to search only the second partition. And I'm going to skip the first partition totally. And the last value in the first half of the data set is 9, which is smaller than the value we are looking for. Hence, we should look only in the second half of the array for a match. So now the last value, so again you are partitioning this one. You are calculating mid for this, and the last value, the mid is 17 here, and 15 is less than 17. So you are going to confine only to this first partition, and you are going to skip this second partition. So the last value of the first half of this very short sequence is 12. Again, if you are partitioning this will be the mid, and it is greater than 12 and less than 17. So there is no match. 15 is not equal to 17 in the second half also. So the search is unsuccessful. 15 is not available in the array. Coming to the analysis of binary search, so let's determine the number of visits to array elements required to carry out a binary search. We always look at the middle element, which counts as one visit. Then search either the left or right subarray, and so on. So we have the time complexity of n numbers is equal to the time complexity only for the one partition, that is n by 2 plus 1, that is the middle element. So by plugging this result into the original equation, we get this as T of n is equal to T of n by 4 plus 2. And it generalizes to T of n is equal to T of n by 2 power k plus k. It can be, k can be here 1 or 2 or 3, like that. So as in the analysis of MEDSORT, we make the simplifying assumption that n is a power of 2. So n can be represented as n is equal to 2 power m. And m value is log n to the base 2. So overall we get T of n is equal to 1 plus log n. Therefore, binary search algorithm became time complexity of order of log n.